All right. Welcome, everybody. Good evening, ladies and gentlemen. Welcome to the Energy Institute and our webinar series, Energy Systems and Digital Technologies. My name is Henry Garcia. I'm a professional in subsurface energy systems, and I'm a member of the Energy Institute, and I'm also part of the London branch. I hope you are all healthy during these difficult times with COVID-19. Seems like we still have some challenges ahead, so please stay safe. For those of you who are not familiar with the Energy Institute, it is the professional body for the global energy industry. And we have more than 20,000 individual members and around 200 company members. And their expertise comes from all different sectors of the energy system and all disciplines, all the way from engineers to technicians to energy managers. And the Energy Institute is a licensed body of the Engineering Council and the Society for the Environment. As energy professionals, we have a big challenge in front of us. Responding to the climate change emergency while meeting the world's energy demands is one of the greatest challenges of our age. So we need more, cleaner, better managed energy, and we need it fast. Therefore, the Energy Institute works to make sure that energy is better understood, is better managed, and valued. And in this context, the purpose of this webinar series is to learn how digital technologies can help raise the bar in the operations in all areas of the energy system, including oil and gas, wind power, methane reduction, battery storage, hydrogen, solar, carbon capture, usage and storage, and integrated networks. And today we have three special guests that will share their experience with us. David Johnson and Jane Wren will deliver the first presentation. And David is the CEO of Kimball, an energy solutions provider based in London. David has worked in the energy industry for over 40 years, performing several leading roles across all energy sectors and all regions in the world. And he's also a chartered chemist with the Royal Society of Chemistry. Jane is the CEO of Atomiton, an industrial AI company based in Silicon Valley. James comes from prior experience in digitalizations as the chief business architect at General Electric, where she headed the industrial internet platform. And before General Electric, Jane was responsible for market strategies at Cisco. And the second presentation will be delivered by David Martinez Rego. David is a co-founder of Data Spartan, an artificial intelligence and data science company based in London. And David is an experienced computer scientist and entrepreneur, and he's also a research associate at UCL. Each presentation will last 20 minutes, followed by 10 minutes Q&A. Please submit your questions to the Q&A panel as you listen to the talks. And without further ado, let's get started. I think the title of the first presentation is Digital, Powering the Energy Transition. I'm going to stop sharing now, and I'm going to make David the presenter. Please, David, you are the presenter now.
Okay. Cool. Well, my screen is frozen. Sorry. Start it again.
Yeah, we can see your screen. Mm-hmm.
Okay, good. Well, good evening, and thank you, Henry. What I'd like to talk to everybody about tonight is how we can empower the energy transition. First, I mean, let's talk about the energy transition itself, and that's referring to the global energy sector shift from fossil-based systems of energy production and consumption, and that's oil, natural gas, and coal, and moving to renewable energy sources like wind and solar. However, as we move forward, we will still need oil and gas. The need to continue to drive costs down and efficiencies will become more and more critical. All the while, we have to balance the need for reduced energy demand and emissions. The current pandemic we face is a global disaster, as Henry was mentioning, but there are some positives from it. It's highlighted the value of communication and joining together to solve critical problems. In addition to managing the outfall from COVID-19, the oil and gas industry is having to adjust to other new realities and the challenges brought about by a sustained low oil price. The presentation highlights the challenges faced and how distributed artificial intelligence supports the oil and gas industry today and the future for the transition to other forms of energy. So I've called the challenges faced must-win battles. These are the key issues that the oil and gas and other industries face within the supply chain. Rightly so, there's a keen focus on energy and carbon dioxide emissions reduction, as well as the carbon footprint. This has to be progressed, while businesses plan to reduce costs and improve their profitability. I think we'll all admit that the use of available information and data has not been well utilised over the years, with the result that many businesses are running at far from optimal levels. You can only cut what you have so far. There has to come a time when there are drives to improve operational efficiency. So what can we do to enable the winning of these battles? Well, we need to establish a digital record and capture information from the physical world to create a digital record of the physical operation and supply network. Things like remote sensors will play a major role in achieving this. We then need to analyze and visualize. Machines, processes, and systems need to talk to each other and share information. This will really allow for advanced analytics and the visualization of real-time data from multiple sources. This data is then applied to algorithms and automation to translate decisions and actions from the data and digital world into movements in the physical world. But there are barriers to move from data to value, and some of these are perceptual, of course, and some of these are real. There are certainly data silos, and some of the reasons are current protocols, formats, structures, frequencies, and not least a lack of security mechanisms. Artificial intelligence is separated from operations, and this is largely because AI models produced by offline tools are not portable to complex and distributed online data environments. And lastly, domain knowledge is underutilized to overcome this knowledge that needs to be captured by structured models and integrated with AI algorithms. Basically, the solutions need to lower the cost of data transformation, create scalable infrastructure to deploy AI, and develop online engines to model domain knowledge. So Jane will talk a minute about a little in more detail about ASTAC, but basically we're enabling devices and machines with any protocol to interconnect and interact securely. The industrial Internet of Things is an evolution of a distributed control system that allows for a higher degree of automation by using cloud computing to refine and optimize the process controls. The IoT refers to interconnected sensors, instruments, and other devices networked together with computers, industrial applications, including manufacturing and energy management. So this connectivity allows for data collection, exchange, and analysis, potentially facilitating improvements in productivity and efficiency, as well as other economic benefits. The predictive analytics allows organizations to squeeze costs out of the operations and ensure that their operations are streamlined and efficient. The potential is huge. In the upstream market alone, McKinsey estimated that there are up to $50 billion in achievable savings globally. So I'll hand over to Jane now to give some detail around what we've been working on.
Thank you, David. So if you can go to the next slide. Yeah, thanks. So as David has outlined, the imperatives are urgent for transition. The opportunity is huge. And the amount of data that the industry has been generating is very large. So what is standing in the gap between being able to collecting, being able to access data, and being able to derive the value or ROI out of it? And that's what part of A-Stack or Automaton Stack aim to do, is to push intelligence or AI analytics as much as possible into the production distributed environment. By that, what we mean that if you look at the last 5 to 6 years, 90% of the work has been to take the data out of the production environment and aggregate it in a center that's offline, remote, and detached from the domain knowledge. Now what we're looking at using this online operating stack to do is to push the software along with the AI models to as distributed places as possible, as in remote pipelines, as in offshore platforms, as close to those pumps and machines and turbines as possible to where the action is happening. This is essential because one is because of the time, the time window of making these decisions of being able to optimize the operations of a turbine is in minute time window, not 6 months later. The second is to be able to capture the contextual and environmental information that are doing there. So the advantage that we bring in having a platform that can run on distributed edges or the very edges of the oil and gas supply chain is to be able to run the AI analytics algorithm in those places, very much in contrast to running an offline data science exploration that may be out of band and offline compared to these operations. Next slide, please. So now, what are the areas that we focus on that can see some very immediate returns and investments? We're talking about the pressure, the economic and sustainability pressure on the supply chain of the energy system. One of the areas that turns out really good, both economic and sustainability return, is to making the energy supply chain more energy efficient by itself. Now, that's going to cover all the way from renewables to upstream and downstreams, but I'm going to just use a case study for a downstream refinery to illustrate the possibilities and the results that we are seeing. So for a refinery to operate on a daily operating budget, for every dollar that's spent on the operations, about 40 cents, 40 to 50 cents is spent on the energy that's spent in transforming the hydrocarbon. And that usually is divided into electricity, generating heat and steam, and direct fuel. There are several areas when we apply predictive analytics using machine learning algorithms that can make substantial changes. For example, balancing the supply and demand of steam being used in the refining process, we usually see 10 to 15% savings right away on multi-billion-dollar steam cost in refineries. Secondly, electricity, depending on where the refinery operates, there are peak charges, peak rates, different kinds of electrical charges from utilities. These can be actually moderated and saved by avoiding unnecessary peaks. Again, coming from real-time intelligence flowing from the machines, where algorithms can find out better ways to optimize different systems or different equipment when they run and the rate at which they run. These kind of algorithms can also detect idling or machines that, or pumps that, or compressors, fans that could be turned at a lower gear, but still running at a higher gear. And then lastly, the optimization of fuel sources. We all know in places like refineries, we have natural gas, we have direct fuel, we have electricity, we may have CHP, etc. And these sometimes are interchangeable. They incur different kinds of carbon footprints and different kinds of costs at different times. Now, this is where dynamically you would want an online real-time system to be able to give you the recommendation that at any time, what is most sustainable and economic to use one of those sources if they are interchangeable. Now, so this is an actual example that actually changed the difference is made for this particular refinery. Now, when we all operate often on set points, and set points has trade-offs. One is, in one way, if you want the set points to be more dynamic, because your demand on energy changes based on whether based on product throughput rate, based on product mix, you would have to manually or using your past knowledge experience to do it. Alternatively, many plants or refineries set points, for example, on steam pressure at the highest possible rate or highest rate to cover all different fluctuations. That always means they're overproducing steam as they need, and you know what steam is, use it or lose it. What AI brings in is a predictive view of the demand, predictive and dynamic view of the demand. So you are no longer reacting to the pressure changes of this moment, but you are looking, the system is looking 4 hours, 8 hours, and 12 hours ahead, and be able to compute the upcoming demand and generate much better optimized set points for these systems, including boilers, including other systems to run, and coordinate them in a more dynamic way. If you can go next, David. So we've seen substantial results in savings. Breaking down, and this is a relatively large mid-sized to large refinery, compare year on year. Savings on an annualized basis over $2 million just coming from the steam energy system itself, coming from two parts. First, of course, using less quantities of steam, not overproducing, not waste. And secondly, being able to more efficiently sourcing from different boilers, from different, whether it's between boilers or CHP system, to use the lowest cost of steam at any given time per kilopound. Now, even more importantly, these kind of reduction in steam or energy use have been converted into carbon dioxide savings, and then we see that's equivalent to taking more than 5,000 passenger cars off the road for a year, or can be used to power households over 2,000 to 3,000 range for a year of households energy. The next one, please.
Yep. So I'll take this through again, Jane. So with respect to what we're bringing is an addition to the economic and energy sustainability model. Digital really is a key driver. And when you look across the hydrocarbon supply chain from field development all the way over to the finished shore markets, there are defined savings that have been identified that can be made in each of these areas. And with deployment of IoT devices and the arrival of 5G fast wireless, it's placing compute and analytics close to where data is created and has really enabled the edge computing. It increasingly allows us to capture value across that whole energy supply chain. And while we're focused here on the hydrocarbon sector, it's equally valuable whether it's in wind, hydro, biofuel, or solar. So just returning to the must-win battles, we are on the edge of a dramatic change in industry as the IoT and digital technology and the use of AI drives the energy transition. As I mentioned, there are barriers that have to be overcome, but the benefits, I think, are clear, as Jane highlighted in that one case. The journey is underway, and the amount of efficiencies, savings, and compliance that can come from this means that laggards will be rapidly overtaken as early adopters reap the rewards of reduced risk reduction, safety improvements, reduction in cost, increased efficiency, and above all, the ability to plan more effectively on their systems to get the most out of the system at any one time with the minimum impact from a sustainable standpoint. So thank you, Jane. Thank you, Henry.
Thanks, David.
Thank you, David and Jane. Thank you as well. And yeah, we have, well, I have a couple of questions. And so the first question is, what are the main challenges when you're trying to implement, an integrated solution like this in an energy asset?
Mm-hmm. Yeah, so I will kind of probably first coming from the kind of ground level, and then maybe David can add that too. So this is a very, the energy industry is a very distributed and diverse industry. So the multitude of data sources, devices, and machines, and pose the first level of challenge, as we saw that earlier, that they naturally create a large amount of silos. That's one of the biggest one. The second one is the separation between a new set of skills and the traditional set of expertise. The folks who are most familiar with how to operate pipelines, refineries, turbines are currently still different from folks who understand AI, analytics, and machine learning. And today there's a tendency to put AI machine learning in an offline corporate center where these data scientists can be separated out from the actual field domain engineering. And that creates what we see at 95% of offline out of band AI that's find it very hard to deploy into the actual production environment and delay the ROI generation. We see that as an urgent thing to not only be able to bring the teams together, but also using platforms and software tools to make sure AI can be deployed into those areas. Just hope that the answers the question. And let me know if David, anything to add, or Henry.
Oh, hello. Yes, I said that we have a question for the audience, and so this is it. For the refinery example, the annual benefit was $2.7 million per annum. What is the associated cost and time frame to implement the solution?
Mm-hmm. Yeah, sure. So the cost is within. The time. So first, talk about time frame. Usually, to stand up a system like this takes about anywhere between 3 to 6 months. It varies, or it depends on the data access from the refineries. For example, some refineries are a lot more data ready in a way that the information, including meter and flow and rest, is already aggregated in single source or several sources. That's much easier. There are less instrumented or less data ready ones where you do need to, for example, add additional flow meters, and that can be the reason that take longer to up to 6 months time window. The cost of this, breaking into a few parts. And first is, of course, the software analytics tools that you will be using. The second is if any hardware instrumentation, and then the third is less tangible, but it does require the couple of folks at the refinery who's familiar with operations to allocate a portion of their time to be able to make sure the project runs, the implementation runs right. So combined with those, you're looking at is between 200 to 400,000 from the year one, and then much lower ongoing cost of maintenance after that. So it's definitely a system that does pays off for itself pretty quickly.
Okay.
Yeah, a good time to plan. Just to in systems where all of the communication is maybe not there in terms of the measurement tools in particular. The way to overcome that in a way is start that planning before coming to a turnaround or planned maintenance, so that you've got a minimum delay in terms of applying anything on the system.
Okay. Thank you, David and Jane. We have another question here. How do you incorporate the change management into your deployment plans?
So I can start, or David, you want to start, or should I start?
Go on, you started.
Yeah, okay, sure. So change management is a kind of one of the most important factors. So every deployment, every implementation like this, first starting from the problem that is defined by the people who actually experience it. And that's a very different approach of a problem that's defined from afar, from a data scientist point of view. And making sure the operators who will directly be making daily decisions based on these AI algorithms are already on board from the time of problem definition. Now, tactically, when we do this, we also do in the last phase of the project plan at least one about 4 to 6 months, 4 to 6 weeks time window for training and process change management, and on a regular basis. But by then, the operators are already familiar with how the AI algorithm, what kind of recommendation they will receive, and if any change or process they will need to implement. We want, and the third part is to be as intrusive and interruptive as possible, which means that most of the AI recommendations are recommendations that can be accepted or approved by operators versus bypassing them, so that there are no surprises in the whole chain of operations. But great question. It's a great part of it, and it's a thing that ensures the success of a project like this.
Yeah, I think one of the key parts, as you mentioned, Jane, is the people side, the education, the inclusion, and the communication part. I'll give an example, a separate oil field application. This was, for example, an application of a chemical that controlled the amount of hydrogen sulfide in a gas stream that, of course, is highly toxic if it gets into the environment. And this was a controlled system, automatically controlled. And in this case, there wasn't a feedback loop. It was more that somebody had to make a physical action based on the forecast that was going to happen. And this was great as you went through the week. But as you got to the weekend and there were less people, then all of a sudden something didn't happen. So you really have to educate people on the why and what needs to be done, because sometimes you can have that whole feedback loop. Sometimes there has to be a manual incursion if you don't have certain parts of the system. So to get the people on board by the education, inclusion, understanding why it's being done, and clear communication and the wins that are there, then all of a sudden the ball starts rolling and it carries through much more easily.
Okay, thank you, David. We still have plenty of questions, but in the interest of time, this will be the last one. But we'll try to answer the questions to the attendees offline, if that's okay. So the last question for you is, does the AI systems integrate the conventional physical models of the system operations?
Yeah, great question. So this is actually a must for AI to do, is to integrate what we call the domain knowledge or the physics of it. And sometimes it can be chemistry models. This is a particularly complex, oil and gas is a particularly complex field. We have seen two different approaches of using AI to do predictive maintenance and asset diagnostics. One is using pure data science only. The second is a combined approach of doing that. The first very often turns out insufficient in diagnosing anything or producing way too much false positives, and because it can only observe anomalies on the data level. When you combine these models, you start to using AI and data science tools to do feature engineering and actually extract those physical models into the analytical view. That has a lot better performance and more specific, but it does require a more higher level of sophistication, both on the platform modeling side and also on the runtime side, because you do need to process more complex streams of data into it.
Okay, well, thank you very much, Jane and David. Really enjoyed your insights, and the audience is obviously very engaged as well. And now let's continue with the second presentation. The title of the presentation is Future Transition to Household Energy Production, the Data Implications and Business Opportunities. And David, you are now a presenter, so please take the stage.
Share. Oh, no. How do I share content is
Just a second, David. I'm trying to make you a presenter here. Robin, are you online? If it doesn't work, I'm going to open your presentation from my side.
So right now, David Johnson is a presenter. He may be able to give the presenter to David. So if you click on David Martinez's name, you might be an option of giving that presenter.
Yeah. Make presenter. You're absolutely right, Jane. Thank you.
Excellent.
My apologies.
oh, that's much better.
You should be able to share now. Yeah.
Is it visible now?
Yeah, we can see it.
Sure. Okay. So really glad to be here. Energy is a topic that I personally like a lot, and you guys in Data Spartan also are very interested in, and I really welcome the invitation. So a little bit about me and about what Data Spartan is. So I'm David Martinez. I co-founded Data Spartan as an AI and data science company that tries to tackle practical problems in the real life with whenever the AI technology is mature enough. In the area of energy, I had a bit of a inner experience when I was doing my PhD. The topic of my PhD was to avoid what is depicted in that photo. So many of, at the time, we started expanding a lot of renewable energy assets. Among them were, most of them were wind farms. The problem with those machineries is that they break a lot. Just to actually break just enough to make the ROI a little bit challenging. So what we did was apply anomaly detection and machine learning back in the days. This was 2008. To try to predict in advance when machinery was gonna break. As Jane was saying, just data wasn't enough, so our final solution was a hybrid between an expert system based on what is on any handbook on vibrations in machinery with anomaly detection on the actual physical signal itself, which proved to be quite successful, and we were achieving times around 1 week ahead before a machine break was going to happen. Which was given enough headspace for the operations teams to go and stop the machine between something like that happening. Moving a bit forward into the present, as I said, I head with other people Data Spartan. We are an artificial intelligence and data science company working in problems involving big data, data platforms, quantitative research in different verticals. We have been researchers in the past and have been doing research in different verticals, maybe telecom, finance, and other kind of areas. And what we do nowadays is we choose very carefully the verticals we attack, where we think we're going to have the most social impact, and where we think that artificial intelligence and the tool sets we have on our hands based on our own expertise are mature enough to actually create an impact. Because AI is mature in some areas, but in some other areas still needs some development to actually have a real impact. So this is the outline of my talk, but maybe I'm a little bit of an outsider because I come more probably I have 10% experience in energy, but 90% on computer science. So I would tend to bring a vision of how good a computer scientists think about the problem. If we have a kind of an internet point of view and thinking about the problem, how would a computer scientist sees it, and how a person who knows about AI and all these technologies will actually see them fit onto the ecosystem. So the first, obviously, the triggers are the climate change and the need for being more energy efficient, because as a society we have become energy hungry and we are consuming more energy than ever, but we are on the most critical point on ever in terms of climate change and pollution. So that's the obvious first trigger. But what we see, this is an analysis, just one of the most comprehensive one I could find for the presentation on what how people are tackling the problem. The first thing we see is that many startups and many companies are trying to solve a specific problem. For example, we have power to X companies who are trying to bring CO2 into other processes, so we consume CO2 and produce some benefit. Blockchain companies, we will see. I will talk a little bit about what blockchain can add to the equation. And one of the main ones that will be the driver of my marrying with AI is energy storage. We're probably seeing a future where our capacity to store energy is going to be improved and decentralized, so we can probably leverage that from the AI point of view. We have demand side management. Well we've seen that's probably the area where machine learning was most applied in the last 5 years in energy. I've seen a lot of initiatives like from the electrical companies here in the UK, with initiatives like Hive, the smart meters, and trying to see trying to advise households on how to be more energy efficient. Vehicles to grid, that's an interesting initiative where they're trying to leverage for the grid benefit the huge energy capacity of the batteries in the cars. We continue creating new renewable energy technologies and more efficient ones. Internet of Energy is a bit of an abstract concept that I think brings everything together, and energy and service is the same. It's very interesting what people are trying to do with quantum computing. I will have one couple of minutes about that. And I think the biggest game changer nowadays is going to be the explosion of distributed energy resources. One last bit about how much percentage reports are saying we're putting on things. Most of it is going into renewable energies and the Internet of Energies, and the other areas like power to grid. Quantum computing obviously is a small percentage because the technology is still not mature enough. Distributed energy resources, blockchain. There is a reason for all those initiatives to have a small percentage in current effort in the industry, and I will try to detail why I think that is the case. So out of all the tools that we have in our hands as a computer scientist, which ones do we think can have an impact in the area, and why? In my view, blockchain technology, AI, big data, and quantum computing probably will have something to do in this area in the next 20 years. So we'll just detail one by one. As a primary blockchain technology, I will try to explain it first, and then I will try to explain why I think it has a point in the area. So for people that come from the outside, blockchain technology you can think of as writing a smart contract is writing a piece of code that is immutable and is available for everyone to know what it does, and we all have to agree what would be the standard protocol that we're going to follow for doing something. Like, for example, tokenization of energy and exchange of energy. We could write smart contracts to tokenize maybe hundreds of kilowatts and start doing an exchange based on a protocol that we all agree. So it's not something that you cannot do with traditional technologies that are not blockchain. But what adds to the equation is transparency and immutability. So the control of what has happened, it becomes more clear and more clean to Big data, in the first presentation I have already introduced it a little bit what the impact would be. So big data just leverages big amounts of computing power into one computer machine, if you may to say so, and it allows for the big amounts of information to flow and to be analyzed on real time or on batch, depending on how you design the solution. What we think is going to happen is that the data that we are going to generate from the energy grid is going to explode. once the amount of actors that start interacting with it becomes bigger. And that will probably come from the household consumer movement that we're seeing. So in order to be able to ingest and manage that amount of information, we're going to need to manage it in a conjunction between algorithms and experts on the field. To make an analogy of areas we work, like for example in finance, finance nowadays is not like finance in the 90s or in the 2000s. It cannot be understood without algorithms. So it doesn't mean that algorithms are managing finance. They are managing the process, because the amount of data and the speed that it flows nowadays, it would be impossible for a human to manage any other way. But it's still humans managing the process. What basically happens is humans manage the process. So these big data platforms, they just allow to manage processes in scale, but a reduced amount of experts who have the expertise and are difficult. So that's what probably the impact is going to be. AI and machine learning. Well, we talk a lot about efficiency, and efficiency can only be achieved if we are able to optimize consumption and production of electricity, because we know there's a lot of loss in transport of energy, and there is a lot of loss coming from processes that probably badly managed in industries that have nothing to do with energy but consume energy. So what AI can help is like this. Two things that are basic pillars of AI is the ability to do prediction problems, like regression problems that try to predict the next step is going to happen, and try to classify situations into a predefined set of classes. Those two capacities that are well mature nowadays can be used to feed optimization algorithms that actually take decisions in conjunction with humans. The problem there is that probably those algorithms have not penetrated enough because of the safety requirements of what energy grids and energy sector itself has. It's a highly regulated environment that it has to be safe. So that's probably some breakers that we have to do to start using algorithms there. And the last one, quantum computing. Still very early stages, but it will probably have something to do. One of the biggest challenges in electricity, as we said, is the planning of consumption and production, but it is also the planning of the grid itself. And to give you like a reference, the latest AI jump that we have experienced comes from the fact of having the new chips that are all of these GPUs that will actually have allow us to jump from something that used to be like quadratic time or cubic time to do it in linear time. And that has allowed us to make technologies that didn't work in the 80s and 90s to actually work, because they can train much faster and we can actually see and do research on them. So what quantum computing does is in some specific cases where algorithms have been put together that can be run in quantum computers, is to reduce exponential time to linear time. So if moving from quadratic and cubic time to linear time has brought us to automated driving and all the applications, automated translations, and all these things we've seen nowadays, we can imagine that in terms of optimizing grids, which is a highly exponential problem, so it's an exponential such problem that we don't have a solution nowadays. Quantum computing can actually help a lot, because by reducing times on finding optimal solutions, we can actually have huge gains. But as I said, it's very early stages, because it's only very specialized people can actually code this kind of computer, so it's still a little bit early stages. So if you put a little bit of internet mindset of how we see things going, this is a very the picture of evolution of probably every household that we have all lived in. Early in the 70s, we had a few appliances and maybe one TV. In the 80s, we jumped to having much more devices for hi-fi, for more TVs at home, more household white goods. In the 90s, we jumped into having the regular household having video games and maybe other devices. And jumping a little bit more ahead, now there's no household who doesn't have probably a couple of tablets, couple of mobile phones, couple of computers, probably a video game system, and more than one TV. So our consumption of electricity in the households has grown a lot, but also has growth It's also depicted here our connectivity to the network and our ability to exchange information from the household to the internet. And people have been in the last decade having got used to actually do a lot of things through the internet and do a lot of things and collaborate in a lot of processes by themselves. Call it trading, call it maybe other processes. What we see the changing happening in the next, probably next decade or next 2 decades is the addition to this household of 3 small changes, but big changes from the energy perspective. One of it is the change of petrol to electrical cars, which is going to increase hugely the consumption that are going to be needed by households. And also the introduction more and more of generation capacity and storage capacity of in the household of energy. And that storage capacity, leveraging the connectivity the households already have to the internet, will actually allow this capacity of storage to be connected to a grid or a communication system where they can actually participate in the process of electricity production, which was not happening before. That has a huge impact, and that's probably where algorithms can help, algorithms and this kind of technologies can help the most. So what will actually allow this transition to happening? The renewable energies are already there and they are government driven, but for the consumption adoption of these things, the problem of these setups nowadays is that they're quite expensive, and for a household, they are, the return of investment is not clear. We're talking about £5,000 investment when the average household energy bill is probably around £500 a year. So we have a ROI of 10 years. So it's going to be very difficult to convince households to participate unless there is any kind of system or any kind of grid that allows them to optimize more their cost thanks to their capacity, or that allows to trade that electricity on any kind of market, which doesn't exist nowadays. And what also is going to happen is they are going to need to connect that capacity to the grid. So that's going to increase the amount of information and the rate of speed that the information is going to flow into the system. So we have the ingredients and we have the problem. Our problem is to try to reduce the loss and cost of energy, and we need to optimize the existing energy generation capacity, but we have this opportunity that the hardware part of the innovations that are coming into this area is allowing us to actually distribute energy storage in many more places than we used to have before, and to also generate power through many more points that we used to have before. We used to be plants generating energy for all the grid. Now we have the grid generating in different points energy by itself. So if you apply like a computer science mindset to it, once you have generated a distributed possibility of storing energy and distributed possibility of generating energy, an algorithm can actually maybe at a local level or at bigger levels can actually look at the data flow and try to see where to pull energy from and how to route the energy to actually reduce the need to actually use sources of energy that are more pollutant, and also to reduce the need to transport energy in long distances, because we can actually have local producers and consumers. So that's something very similar to, for example, what our logistics sector does nowadays. When you have to move a lot of goods, there is actually optimization algorithms and technologies that are already mature there, that leverage AI to do the forecasts of where things need to go and what is going to be the delays and everything, and then you put it together in an optimization algorithm that is running in real time. So every 5 minutes or so, it helps take decisions on a big scale. So just to summarize a little bit on the 4 pillars of technology and how they can impact, I think within the blockchain technology is probably going to impact more at the financial level. So since these exchanges of energy haven't been created yet, and are yet to be developed. Probably they will adopt blockchain technology because of the transparency and efficiency in terms of developing software systems that they are allowed to. Probably the blockers for them to develop will be that these technologies have a problem on security. So it's very difficult to come up with these smart contracts that are secure to be used, because the code can be seen. It's very difficult to avoid it to be exploited. So we probably will need a big consortium to come together to make a big effort to create these smart contracts, but it's not something technology cannot achieve nowadays. It can be achieved. In terms of AI, I think AI will actually marry more with the distribution network of energy, and it will probably combine with optimization algorithms to reduce the transport of energy and to reduce the problems of we're going to see the energy bottlenecks. Big data is going to be the fabric, so this data needs to flow. So you need to be able to connect your household battery to some system where data is gonna be fed, and where and it's gonna be exploited. So nothing of the on the blockchain level or the AI level can happen without having fabric built on current big data technologies that allows this data to be managed. And as I said, quantum computing will probably take another 10 to 12 years. But the impact that it's going to have probably is more at the decision level. It's going to be able to allow us to see opportunities of optimization in the whole grid that are actually difficult to see nowadays, because as I said, these kind of optimization problems are exponentially computationally. So we're actually not seeing the optimal solutions yet. Obviously, nothing comes without risks. I think the introduction of all these new participants in the network is coming with risks. We saw what happened lately, for example, in the financial market, when people have realized they can actually collude together and move some stocks and move the market just by orchestrating the behavior. So that cannot happen. If you connect all the households, that is a potential. That kind of risk become a potential and a potential reality. So we will have to be able to mitigate that, and that's probably the reason why it's very difficult for these algorithms to be deployed, because regulation have to ensure the safety of everyone. So what we probably think will happen is something similar to what's happening in the financial sector, where many countries are setting up sandboxes where these advanced ideas can be tested in a small scale in a way that doesn't put into risk the whole grid, but we actually can start leveraging the experience to actually see what works and what doesn't, because these algorithms, like these deep learning algorithms, regression, all these maths are generic tools that they need to be applied on the real data to be able to be effective. And we need to see first working before we actually deploy it. And it's impossible to predict which tool is going to work without seeing it with the real data. So there has to be the regulation, and the actors have to allow that for happening, even if it's in a small scale, for all these tools to actually be deployed. Otherwise, we will only touch the surface. We will only be able to touch maybe at the analytics level or in a very not in a deep way into the energy. So just one final thought. We all have to adapt, and probably all the actors in the area will have to adapt. I don't think there is going to be a stop on this movement, because, as I said, the request for electrical energy is going to be the more and more demanding, and we are going to need to adapt the grid for the introduction of all these electrical parts. And at the same time, we have to reduce our CO2 emissions. So there's no way we're going to stop it. And I think the solution is going to be in the marriage between households and data, being able to collaborate to actually becoming self-service and efficient, and the big producers of electricity and the big plants actually becoming available to for the demand of industry and the transport that's going to be.
All right. Thank you, David. Very interesting presentation looking into the future of the smart grid and prosumers. We have time for a quick question. And basically, I would like to ask you, what are the key steps to make the smart grid with prosumers possible? What do we need to get there?
Well, first of all, I think, as I said, I see the blocker of the role in the house. We have to get them engaged, and for that, they have to see a real benefit from this point of view. So I think we have to create systems that allow them. Some people is trading cryptocurrencies nowadays and in trading other assets. They will be able to decide, okay, if I install these in my house, I can actually contribute, but I can actually also get a return on investment that is not 10 years, that is maybe 5 years. The second block is actually to adapt the regulations and adapt all the grids so they can introduce these en masse. There's been initiatives that are, for example, in Germany, and now they're starting in Spain, where they're testing that out in specific communities, but we still haven't actually probably thought how it's gonna all be together. So what is the standard system to become part of this consumer network? Who are going to be the technology providers? How is this going to be regulated, and how is this going to be safe? So for me, the most important things are the return of investment for households and safety and regulation.
Okay.
But on technology side, I think technology is mature enough to achieve probably 80% of it already.
Okay. Well, thank you very much, David. I think we're reaching now the end of the webinar. Could you please make me the presenter? So I can share final remarks with the audience.
Maybe institute host. I hope I choose the wrong one.
Is the other one? There are two. Try the other one.
There were two options. Now it's
Yeah.
the right. I lost the presenter.
Okay. So can you see my screen now? Oops. What is the PowerPoint? Well, I think I unintentionally closed the PowerPoint, but I want to thank you all for participating in this webinar. Thank you to the panelists for your insights on how we optimize existing physical energy assets and what the future of energy assets will look like. You can find Kimball, Spartan, and Atomiton on the websites and on LinkedIn. If you are not a member of the Energy Institute and want to join, please visit the website for the details. And if you want to join share your story with the London branch of the Energy Institute, please do get in touch. You can reach me at londonbranch@energyins.org, or you can always find me on LinkedIn. And my ID is Henry Garcia, Energy Systems. And yeah, I wish you all the best, and stay tuned because we have more episodes coming. Thank you very much, and please stay safe. Bye-bye.